Any questions about anything? Yes? You're going to get a homework assignment today or tonight that's due late next week. It's on the sinusoid, the stuff we've been doing on the sinusoids. So yes, and the TAs are working on the whole office hour thing. I nudged them last night because I hadn't heard back from, I'm going to try to turn these guys off. Let's see. These very expensive projectors are bothering me. There's one. See, this is a phasor with an E as opposed to a phasor with an O, like we talked about last time. Okay. Any other questions? OK, great. So anyway, we are talking about these pure sine real valued pure sine signals, sinusoidal signals. And given such a thing, we can always represent it as follows. X of t is equal to a cosine 2 pi f0t plus phi, where, assuming x of t is not the zero signal, a is positive, f0 is positive, and phi is in the interval minus pi to pi. And if we're given it with a phi that's outside that interval, we can always adjust it by sliding it by integer multiples of 2 pi. And we can always write it that way. And we talked about various things. Like, for example, if you shift one of these, you get another one. If you have a sine instead of a cosine, you could turn it into a cosine, all that kind of stuff. And at the end of class last time, what we were doing was we were targeting the following key fact, which is that if I take any kind of a sum of these things where you have the same frequency but possibly different amplitudes and phases, you can always collapse that and rewrite it as a single one. All right, so the fact is that if x of t is, say, the sum from k equals 1 to n of, say, ak cosine 2 pi f0t plus phi k, this guy, f0, is the same for every term. So same f0 in every term. You can rewrite x of t as some a cosine 2 pi f0t plus phi for some positive a and some in minus pi to. So you can take a sum of these things and rewrite it that way. Now, that's not, to me, obvious, but how we're getting to that is by means of this idea of phasor amplitudes. So we did this little detour. So we did a little review of complex numbers. And we noted at the end of class last time that for any of these terms, for the kth term, we can express it as follows. So this is the way we're given it. We're given it as ak cosine 2 pi f0t plus phi k. We can write that as the real part of what? Well, because of Euler's formulas, this from our review of complex numbers, this is the same as the real part of ak e to the j 2 pi f0t plus phi k. And if I factor the e to the j 2 pi f0t out of what's inside there, I get this, ak e to the j phi k times e to the j 2 pi f0t. And if you write this guy, just give it a name, real part of, say, cap xk e to the j 2 pi f0t. That's a way of writing that kth term in that expression. And we call xk, which is just ak e to the j phi k, the Phasor amplitude of the kth term. Okay? And if I rewrite every term in terms of its Phasor amplitude by writing it as real part of xk e to the j phi k, what happens for x of t? So x of t is going to be the sum of those guys, sum k equals 1 to n of ak cosine 2 pi f0t plus phi k. And writing every term in this Phasor amplitude-y kind of way, I get this as sum from k equals 1 to n of the real part of xk e to the j 2 pi f0t right? Does everybody believe that? And the sum just slips inside the real part. So I get the real part of, parentheses, sum from k equals 1 to n of xk times e to the j 2 pi f0t. And if I call this guy in parentheses, call this x, cap x, then we see that x of t is real part of complex number times e to the j 2 pi f0t. So this is like the Phasor amplitude of x of t. And if we write x in polar form as a e to the j phi with a positive and phi in the interval minus pi to pi, we get x of t equals real part of a e to the j phi e to the j 2 pi f0t, which is just real part of a e to the j 2 pi f0t plus phi, which is just a cosine 2 pi f0t plus phi. So that proves our basic fact. Now let's summarize this. The summary is as follows. And it's always good to have summary, have things in words and equations. These parallel universes of words and equations, it's good to keep a foot in each one. So in words, the sum of a bunch of pure sines, pure sinusoids, pure real-valued sinusoids, real-valued pure sinusoids of the same frequency is a pure sinusoid of that same frequency. Furthermore, the Phasor amplitude of that sum is equal to the sum of the Phasor amplitudes of the individual terms. Okay, so that's that. Now, if someone came up to you in Hope Plaza and presented you with a complicated sum of phase-shifted cosines of the same frequency f0 and asked you to write it as a single cosine of frequency f0 in some phase and some amplitude, what would you have to do? Okay, so here's a problem, and here's where the work is. Here's where the work on the homework is, okay, basically. So if someone presents you with this sum, x of t equals the sum from k equals 1 to cap n of ak cosine 2 pi f0 t plus phi k, how to find a and phi such that x of t equals a cos 2 pi f0 t plus phi, question mark. Well, the answer is right on the board. You just find the a and the phi by first finding the Phasor amplitudes of each term, adding them together. So first, compute x to be the sum from k equals 1 to cap n of xk, which is the sum from k equals 1 to cap n of ak, e to the j phi k. Then, and this is the hard part. This is the hard part, because in general what's going to happen here is you're going to have ugly expressions to put together. Then you write x in polar form, a e to the j phi, i.e. in polar form. This is the quote-unquote hard part. And finally, you have x of t equals a cos 2 pi f0 t plus phi, where a and phi are from that expression. So let's do an example and see why that's, in general, it's not the easiest thing in the world to do. Okay? So quick example, if I can get this new box of chalk open. I might not be able to. Does anyone know what course Professor Kresgaza is teaching in here before this class? What, that had probability on the board? Does it have to do with the... Sorry? OK, autonomous mobile robots. Cool. Because I knew it was probably about robots, but I wasn't sure, because I know she's a robot hotshot among many on the Cornell faculty, including our own Professor Kirsten Peterson. OK, so here's an example. How about this? How about, I'm just going to pick some random numbers. Say x of t is equal to, say, 7 cosine 2 pi times 19t plus pi over 7 plus, let's not use 7 twice, say pi over 3, plus 11 cosine 2 pi. Remember, they have to be the same frequency, so we have 19 in there, minus, say, pi over 11. No, don't use 11 twice. 5. How about that? Someone gives you that. It says, write this as a cosine 2 pi 19t plus phi. How do you do it? You find the Phasor amplitudes of the individual terms. So the Phasor amp of the first term is going to be, so the Phasor amplitude of x of t is going to be cap x equals Phasor amplitude of the first term, which is 7e to the j pi over 3, plus the Phasor amplitude of the second term, 11e to the minus j pi over 5. So these are the Phasor amplitudes of first term and the second term, respectively. OK, so far so good? Now, we know that, like, we know how to do cosine and sine of pi over 3. But I don't know by heart cosine and sine of, like, pi over or minus pi over 5. Does anyone know those by heart? No. OK. And so in general, what we're going to end up doing is we're going to find the polar form. So find x in polar form. Generally, what we're going to have to do is assemble these guys together first in rectangular form. So first, merge the pieces, the terms, in rectangular form. And by the way, I hope that the review of complex numbers wasn't too brisk for anybody, and that I can throw around terms like rectangular form and polar form with reckless abandon and not have folks, not have to give trigger warnings or anything like that. But anyway, what we do is, so x is equal to 7 cos pi over 3 plus 7 j times 7 sine pi over 3. This is by Euler's, plus 11 cos pi over 5 minus j times 11 sine pi over 5. So that's by Euler, right? And in turn, you see the real part of that is going to be the sum of the first and third pieces. So x is equal to this. So 7 cos pi over 3. What is cos of pi over 3? It's 1/2 plus 11 cos pi over 5. I don't know that one by heart. Plus j times 7 sine pi over 3, which is square root of 3 over 2. So 7 square root of 3 over 2 minus 11 sine pi over 5. Great. We have x in rectangular form. And from this, we can find a and phi. How do we find them? Well, we have to find the magnitude of x. The magnitude of x is the square root of the sum of the squares of these guys. So it's going to be 7/2 plus 11 cosine pi over 5 quantity squared plus 7 square root of 3 over 2 minus 11 sine pi over 5 quantity squared. All that to the 1/2. And what's phi going to be? Phi turns out to be the arctan of imaginary part over real part, moved if necessary, so it's in minus pi to pi. So phi turns out to be tan to the minus 1 of 7 square root of 3 over 2 minus 11 sine pi over 5 divided by 7/2 plus 11 cos pi over 5. Ugly numbers. OK, so, well, I shouldn't say ugly. I mean, ugly is kind of pejorative. They're kind of vaguely unattractive. How about that? Sort of unprepossessingly plain. I don't know how to diplomatically call a number ugly to its face. Numbers have a way of getting back at you if you're mean to them. I've discovered this on many tests. So be careful what you say about numbers. So these are vaguely unattractive. They're not pretty, but that's the way most problems are going to come out, unfortunately. Most problems, it takes a lot of time to design a problem where all the cosines and sines are like, things like 1/2 and square root of 3 over 2, and they divide out nicely. And the book doesn't do that. I don't do that because, you're grown-ups and you can handle it. All right, so anyway, this is an important fact, that if I take any sum of same frequency sinusoids, real valued same frequency sinusoids, I can write it as a single one with its own Phasor amplitude, with its own amplitude and phase. That's a cool thing. And to me, that's not an obvious fact. All right? OK, so what if instead of this, we write a sum of real valued pure sinusoids that don't all have the same frequency? What happens then? So how about some other combos of sinusoids? So how about sums of pure sinusoids that don't all have the same frequency? what can we do with those? Well, it turns out not really much from a signal standpoint. What's the general form of one of those going to be? So for example, x of t, how about this? It's going to be some number a0, a real number a0, plus the sum from, say, k equals 1 to n of ak cosine 2 pi fk t plus phi k. So again, we're allowing each of the terms to have a different amplitude, but these are not all the same. And why am I allowing a real number out there? Well, we mentioned last time, we noted last time that you can think of any constant as a zero frequency cosine with amplitude, the absolute value of that constant, and phase either 0 or pi, depending on whether the constant is positive or negative. Okay, so we'll come back to that. But anyway, that's the kind of x of t we're going to be thinking about. So what happens when you add those together? What do you get? Well, in general, this is going to be a pretty crazy signal, even just for a few terms. It's not necessarily periodic. So generally, x of t isn't even periodic, much less a pure cosine, a pure sinusoid. And if you graph these things, if you just play around with this and do a few examples, like on MATLAB or whatever, and look at the graphs can look pretty crazy. Graph of x of t can be really complicated. But clearly, by representing it this way as the sum of just a bunch of terms, there's only a few parameters relevant to specifying x of t. If you wanted to describe this x of t to somebody, you wouldn't have to give them this huge complicated graph. You would just say, oh, well, it has a constant term of value a0, and it has a bunch of cosines of those amplitudes and frequencies and phases, and that's that. Okay, but really, we'd like to be able to do something graphical to embody that data compression, so to speak, of describing the signal in terms of these few parameters. So what do we do? Well, it's customary to describe this thing schematically in terms of what's called its two-sided spectrum. Okay, so it's customary to do a graphical representation, do a simpler graphical representation. So by means of what we call its two-sided spectral representation. Or just plain spectrum. And the word spectrum is cool. I mean, you've all heard the word before. If you live in New York State, you're enslaved by the company Spectrum, which, or this part of New York State, which does our cable. But, you've heard of spectrum before. It's like, the colors out of the prism and all that. And where does the word come from? What is the Latin root? Whatever. Well, spec has to do with things like vague reflections or ghosts or mirrors, things like that, like specter, right? You've all heard of specter as a ghost, right? And in Italian, like the word for mirror is specchio, So every time you see spec, you can think about like that. But anyway, this is going to be an important focus of our way of analyzing signals over the course of the semester, is to give them another kind of a representation, a two-sided spectral representation. So first, I'll go through the nuts and bolts of that, and then talk a little more about the the philosophy and the math behind doing it. So how do we do this? What we do is we take x of t and we use Euler's formulas to write each of the terms as follows. So we rewrite x of t as a0 plus, and for each term, I'm going to separate it into two pieces. There's various ways of going about this. This is just one way. This is the same as x of a over 2, ak over, excuse me, ak e to the j 2 pi fkt plus phi k over 2 plus ak e to the minus j 2 pi fk phi k over 2. Now, why is this the same as that? This is, we remember, this is equal to ak cosine of this plus j sine of this over 2. This is ak cosine of this minus j sine of this over 2. So when I add them together, I get ak over 2 cosine this twice. OK? So this is by Euler. And specifically, it's the whole thing, real part of z equals z plus z conjugate over 2, along with e to the j phi, or e to the j theta, conjugate equals e to the minus j theta. So that's step 1. Now, step 2 is you separate these into plus and minus fk terms. So you have a0, and let's rewrite a0 as cap a0 e to the j phi 0. How do we do that? a0 is absolute value of little a0, and phi 0 is equal to 0 or pi, depending on the sign, sign, not sine, of a0. So this is plus the positive terms, so the sum from k equals 1 to n. And I'm going to rewrite each of those as follows. ak e to the j phi k over 2, e to the j 2 pi fkt. And the negative k, the negative frequency term, so sum from k equals 1 to cap n, ak over 2, e to the minus j phi k, e to the minus j 2 pi fkt. And now what do? We take this and we turn it into a picture. And the picture we're going to draw is a Stemplot. What do? We draw f space. And remember, this is not really a graph. It's a schematic thing. Here's f space. This is the f-axis. Here's f equals 0. And how do we turn that guy into a Stemplot? Well, first we put something at 0 frequency, which corresponds to the 0 term, the a0 e to the j phi 0. So this is what we do. We draw a little stem here, and we write a0 e to the j phi 0 there. Then we look at the other terms. So say at frequency f1, we put a stem here, like so, and we put a1 over 2 e to the j phi 1. And then at f2, say f2 is out here, we have another stem. The stems all point up. It's an optimistic kind of a picture. OK? Here we have a2 over 2 e to the j phi 2. And they may be out here, say at f3, might be here. You might have a little teeny little stem, A3 over 2 e to the j phi 3. And you have over here, in the negative f space, the same things except one difference. The SIGNs of the phases of the phi terms are the opposite. So here we have at minus f1, a1 over 2 e to the minus j phi 1. And at f minus f2, we have the tall one, a2 over 2 e to the minus j phi 2. And then at f3, we have the little guy, minus f3, I should say, a3 over 2 e to the minus j phi 3. So that's how we turned this into a Stemplot. And oh, it's amazing how bad my drawings are sometimes. These are supposed to be the same length here. These are supposed to be the same length, you know, all that kind of thing. OK, so what about the stems? How do we make the stems? Well, it's easy to see how we labeled the stems. What are the lengths of the stems going to be? The length of each stem is going to be the magnitude of the label on it. So the length of each stem is equal to the magnitude of its label. Now, its label is basically half the Phasor amplitude of the kth term in the original x of t. OK, so each stem label is essentially either the complex conjugate of or the actual thing. So it's either the Phasor amplitude over 2 or minus. This isn't worth saying. Just say that. Don't you hate it when people come up to you and say, oh, no, never mind. You know. Doesn't that bug you? OK, its label. So for example, if A1 is smaller than, in this picture, A1 is smaller than A2. And notice that the e to the j phis don't contribute to these things. Never answer a toll-free number. Calls you during class, especially. So the e to the j phis don't contribute to these magnitudes. Why? Because, as we noted last time, magnitude of e to the j theta is equal to 1 for all thetas. Can't emphasize that fact enough. Goes under folks' radar. But anyway, that's what's called, oh, and the toll-free number left me a message. And I bet I know what it's about. We'll check during the break. But it's probably one of the, I don't know how many of you get these, but it's a voice speaking Mandarin telling me to get down to the embassy right away because my passport is about to be revoked or something along those lines. OK, do you get those, Alex?
You're always like, some suspicious activity has been detected on your social security number.
Well, there's that. But the ones I usually get from toll-free are the Mandarin warning ones. You know.
And it is still a toll-free number. Call it.
OK, fine. Now this is the two-sided spectral representation of x of t, and you're going to have a pair of stems for each of the terms in the original signal x of t. So for each cosine term in the original x of t formula, you have a pair of stems. OK, one of them is going to be at frequency fk, and one is at frequency minus fk. And the label of the fk stem conjugate is equal to the label of the minus fk stem. So there's this conjugate symmetry going on, and this is something that pops up all the time. You know, we have lots of things that tend to be conjugate symmetric when we're dealing with real valued things. All right, so this is the two-sided spectrum of a finite sum of cosines. And you may say, why? Why even bother getting, why? Yes, question.
What do you mean by label?
These are labels.
So, do you mean the? Oh, I see.
Yeah, the stem plot is going to be stems. They're going to have lengths, and they're going to have labels. Okay, that's what I meant. Yes, question? No, it's not x of t. And I'm trying to get to, yeah, what is it? This is a really good question. What is it? It's a stem plot. That's about all it is. It's a way of describing x of t in a compact fashion. It's a schematic kind of thing, okay? And this is what I meant by getting to the sort of the math and the philosophy of why we do this, okay? So this is a really good question. Really good question. So what is this? What is this two-sided spectrum? Even. Okay. It's not a graph of x of t. Emphatically, it's not a graph of x of t. However, it exhibits all the parameters that you need to describe x of t. It exhibits all the a's, all the ph's, and all the f's. And those are exactly what you need to describe the signal x of t. So it exhibits all the parameters, the ak, pk, and fk needed to describe x of t. Because remember, x of t is just this. Needed to describe x of t. All right, so the thing is, like, this is something, another thing that goes under people's radar is this picture does not just tell you something about x of t. It tells you x of t completely. It tells you everything you need to know to completely construct x of t. So thus, this two-sided spectral representation is a complete description of x of t. It's not just describing something about x of t. So it doesn't just, quote unquote, tell you something about x of t. And I'll put something with a squiggly underline under it to emphasize that's how you have to say it. It tells you something about x of t. It tells you everything about x of t, but in a different way than writing it as a time function. Okay, and so another piece of terminology that folks use when alluding to spectra, spectra, by the way, is the plural of spectrum. People call it a frequency domain description of x of t, as opposed to time domain description which is the way of writing x of t as a time function, or perhaps as a graph as a function of t versus t. So these are words that you're going to learn to use. And it's not, by the way, it's not just sums of sinusoids that have these frequency domain descriptions. It's lots of other signals too. And I'll try to dig into that a little bit as we go along. But I want to emphasize it's a complete description of x of t. It just tells you all about x of t in a different way. Now this kind of a thing happens all the time in real life, where you have two expressions that describe the same object, but they seem to be talking a different language or emphasizing different things. Like, for example, like if you want to describe like my house in Ithaca, you could say 410 Mitchell Street. Okay, there I gave you my address, so you can throw eggs on Halloween or whatever. Okay. Or you could say the White House with a hedge in front of it that's like 3 up from the intersection with Ithaca Road on Mitchell Street. Okay, those are two expressions describing the same object in the real world. But they use completely different language. You know, one of them is talking about like an address. You know, like in C it would be and whatever, right? Ampersand whatever. The other one is talking about like is talking about what color it is and where it is relative to some corner. But they describe the same object. So a philosopher would say these terms are coextensive. They have different intensions but the same extension. Oh, you don't want to know that level of detail. Okay. Bottom line, though, is that the time domain and frequency domain descriptions of a kind of a signal like this, x of t, are coextensive expressions. Okay. So let's take the 3-minute break, and then we'll move on with this and talk about other ways of combining cosines and how what they lead to spectrally. Okay. Here's the question. Like, doesn't the the graph tell you the same thing the right side of the graph except with a minus sign on the phis? Like, do I gain anything by having two sides of this graph? If I just have the one side of the graph, I could reproduce the second side and vice versa. That's very true, okay? But that's one of the reasons I said it's customary, I forget where that word is, to do it this way, because this is the way people do it. And one of the reasons they do it this way is one of the properties of spectra, and that is that if you take a sum of two signals, then their spectral pictures just add together. And if you do just the one-sided one, it gets more complicated. Okay? So that's one sort of mechanical kind of like utilitarian or pragmatic reason to have a two-sided spectrum. But yeah, that's a good point, that mathematically speaking, the left side tells you nothing more than the right side does. Okay, yeah.
Would the units for the y-axis be related to whatever the function represents?
No, not at all. You just make them whatever you want, just so you can fit all the stems in. Yeah, yeah. Did everyone understand that question? Like suppose x of t is a voltage or something, right? Or it's in kilovolts versus volts. Like, is there something about the y-axis that should show that? And my answer to that is no, there isn't. You know, just forget about the units. Just think of it as a mathematical function of time. Yeah.
So is the spatial orientation that you drew it in, is that irrelevant, or is that?
You mean why not do it this way?
In terms of like the space between like the axes and F1, and like where they are.
Oh yeah, I just picked random spots to put those. Yeah, I just wanted to make it look like they're not all the same, and that there may be like not even rational multiples of each other, or you know, whatever. Cool. Okay, so anyway, we have this frequency domain way of describing these sums of cosines. Now here's a fact, and this is something I just mentioned when I was answering her question over there. So here's a fact, that if you have two signals and you add them together, so if, say, x1 of t and x2 of t are both signals of this form, and if you take their sum, or let's take an arbitrary linear combo of them. Say x of t equals, say, c1 x1 of t plus c2 x2 of t. Then, and I'm going to write this out in words. Again, this is the parallel universe of words first, and then we'll do an example where we actually do it with numbers. The two-sided spectrum of x of t equals c1 times the two-sided spectrum of x1 of t plus c2 times, and I'll put times in here, the two-sided spec of x2 of t. So let's do a quick example. How about x1 of t is equal to, say, negative 3 plus 7 cosine 2 pi times 19t plus pi over 3. And x2 of t is equal to cosine of 2 pi times 19t. I put the parentheses to be consistent. Minus, or let's say plus 13 cosine 2 pi times, say, 31t minus pi over 5. OK, so those are two perfectly good signals, right? First, I'll do the, and say x of t is equal to, how about x1 of t plus 2x2 of t. That's a good one. OK, so let's figure out the spectra of x1, x2, and x. So spec of x1 is going to be this. It's going to be minus 3. You have a constant term. So what do we put at 0 here? How long is our stem? 3. And what do we label it? Who said 3? OK, and what?
E to the power of j 0.
Say one more time.
3 times e to the power of j 0.
0, because we have a minus sign in front of the 3.
Oh, pi.
Pi, yeah. So this is our stem at 0, like so. And the e to the j pi just indicates that the constant term is negative. All right, and then we have a stem at 19. And what length is that stem going to have? So say this is 19. We're going to have a stems at plus and minus 19 that have the same length. And what's that length going to be? You know, this is kind of mean of me because I just erased the picture that you would figure that out from, right? OK, well, let's try somebody else. Yeah, Nicholas. 7 halves, exactly. And what's this? And so 7 halves, that's not much bigger than 3. So let's put that there. 7 halves length. And what is the label on the right-hand one going to be?
7 halves e to the j pi over 3.
Yes. And the one over here, what's? No, go ahead. Go ahead.
7 halves e to the negative j pi over 3.
Yeah. OK. Excellent. And finally, well, that's it. That's it for x1. What about x2? Here's the spec of x2. So you have a cosine of 2 pi 19t. So that means we're going to have a stem. I'm not going to ask you to do these because I want to move on. A stem of length 1 and label What's the label on that one going to be? The ones that stems at 19. Anybody? Yeah.
30 would be like 30.
OK, remember, we're looking at this term. We're looking at this term. OK, that term gives us the stems at plus or minus 19.
Would it be like one half e to the j will be 0, so.
Yeah, it's 1/2 e to the j0. You got it. 1/2 e to the j0, which is 1/2. Awesome. And so this is not to scale. So this is 1/2. And 1/2 over here as well. There's no phase, or 0 phase. And then out here at 31, we have a stem that's going to be length 13/2, which is about 7. So it's 13/2. E to the minus j pi over 5 is going to be the label on this one. And minus 31, you're going to have 13/2 e to the plus j over 5. And finally, x of t being x1 plus 2x2, you can just take those two spectra and add them together as follows. So this is the spec of x. So you're going to have constant term here, so 3 e to the j pi. And then you're going to have, oh, we have 19s coming in both terms. So we have at 19, we have 1/2 plus 7/2 e to the j pi over 3. I have no clue what the magnitude of that is, so I'm just going to draw a random stem. So 1/2 plus 7/2 e to the j pi over 3. At 19, at 31, you're just going to have, say, 13/2 e to the minus j pi over 5. And over here, you have just the reflections of these. Like so. Now the cool thing, now this is, by the way, this is back to your question. You know, why do the right hand and the left hand side? Like, if I just added these two guys together, well, you know, it doesn't really save that much work. But I was going to say it's hard to see how, you know, to put these two together, how do you figure out the length of the thing? But you just take the Phasor amplitudes and add them together and divide by 2. So anyway, that's one thing about spectra, that they are kind of linear in the signals you're expressing. Yes?
Are you just adding them together?
Oh, I forgot the 2, right? So let's fix that. This is going to be 1 plus, how about that? And this is going to be 13 with no half. Thank you for that, fixing that error. Unfortunately, we can't go back and change the video. So for posterity, we can blur my face. You know, like, everybody see what the error was and how I fixed it? x1, or x of t is not just x1 plus x2, it's x1 plus 2x2. So I needed to multiply this spectrum by 2 before I add it to this one. And that's why the 1/2 becomes a 1, and the 13/2 becomes a 13. Very good. Good spot there. OK. Now I want to talk about a couple of other ways of putting sinusoids together that the book talks about and what they look like spectrally. So here's two, and these examples are related. So two related to each other examples of putting, quote unquote, putting sinusoids together and what's happening spectrally with these examples. The first one is something I'm going to call a beat signal. This is what the book calls it. So a beat signal. I'll put that phrase in quotes. So this is not like, you know, beats as in not what the MC does, you know, whoever is doing that. It's this. X of t, and you can do this with phases too, but I'm going to do it with no phases. OK, so we can do it with so for ease of exposition, we're going to leave that for the homework. X of t equals, say, how about this? How about cosine 2 pi f0 t plus, or times cosine of 2 pi f1 t, where f1 is much bigger than f0. Now, why do we call that a beat signal? Well, if you graph this as a time function, what is it going to look like? So why the name? So if you graph it versus time, x of t versus t, and this really is a graph, unlike the spectrum, which is a schematic representation, this is what it looks like. You're going to have first off, you're going to have a cosine of frequency f0. I'm going to dot that in. So this is going to be cosine of frequency f0. I'm just going to dot that in. It's not part of the graph. I'm just going to dot that in like so. Reminds me of those TV shows when you're a kid learning how to draw. Never worked for me. Whatever. Made it look so easy. So this dotted picture, the dotted picture is a cosine of frequency f0. And inside this dotted thing is going to be a much faster cosine. Frequency f1, and it's going to go like that. So this is what's going on with this signal here, and I'll write some things down next to it. So that's all supposed to be the same. OK, so the dotted graph on the outside is equal to cosine of 2 pi f0 t. The up and down thing on the inside. So this is like sort of like the envelope of this in a way. And the graph inside, the fast varying graph of x of t itself is going to be, quote unquote, a cosine of 2 pi f1 t whose amplitude gets governed by the cosine of 2 pi f0 t. OK, so why do we call this a beat signal? Well, here's why. And we're going to be talking a lot more about music, and I'll bring in the keyboard from the lab, and we'll explore things like that as we go along. But roughly speaking, it's going to turn out that you can think of a musical note as a periodic signal of some fundamental frequency. And that fundamental frequency is the pitch. of the musical note. And if you think of cosine of 2 pi f1t as a musical note of frequency f1, pitch f1 hertz, then multiplying it by that slow cosine, cosine 2 pi f0t, it sounds like that same note, but the volume goes up and down and up and down and up and down. So the reason for the name, think of cosine of 2 pi f1t as a musical note of frequency f1. So this is like pitch. Then x of t sounds like, quote unquote, that note waxing and waning and waxing and waning and waxing and waning in volume etc. with quote unquote beat frequency, and I guess I have to use single quotes because this is an embedded quotation, f0. Okay? So if your note is like then what does x of t sound like? It sounds like Get it? That's why they call it beat, right? Okay, so I promised you that when we do these examples, we're not going to just talk about, the thing as a time function. We're going to see what's happening with them spectrally. So what's happening spectrally with this one? What does the spectrum of this one look like? So spectrum-wise, how do we find the spectrum of that signal? It's not a sum of cosines anymore, right? It's no longer a sum of cosines. We could use high school trig identities to turn this into a sum of cosines. But I don't remember those particular trig identities, the ones for a product of two cosines. Do you remember them by heart? Anybody? OK, so what do we do instead? What do we do instead? We go through a process that I call, and we made this up last semester. It's a new term, a new highly technical mathematical term here. We figure out by what I call going full Euler on x of t. So how does one go full Euler on something? One takes every cosine in sight and expands it as a sum of complex exponentials, and then does all the multiplication, and boom, you've got whatever you're looking for. So you expand every cosine in terms of things like e to the j theta. OK, so I'll give you an example how to go full Euler on this. So x of t equals, what is the first term? The first term is cosine 2 pi f0 t. That's the same as 1/2 e to the j 2 pi f0 t plus 1/2 e to the minus j 2 pi f0 t. And the second term is 1/2 e to the j 2 pi f1 t plus 1/2 e to the minus j 2 pi f1 t. So that's the first step of going full Euler on something. You take every cosine and you expand it using Euler's formula into a sum of e to the j theta type things. And now we multiply them out. What do we get? We get 1/4 times everything. And I always forget the 1/4. So if I do, so we're going to get 1/4. And I'm going to write them in descending order of frequency. E to the j 2 pi f1 plus f0 t plus 1/4 e to the j 2 pi f1 minus f0 t. Those are the ones with positive frequency. And the other ones are going to be 1/4 e to the minus j this, j2 pi minus f, or e to the j2 pi minus f1 plus f0. Is that the same? That's right. T plus 1/4 e to the j2 pi minus f1 minus f0 t. And why did I do that? Well, these give us the spectrum because, so this is f, spec of x, looks like this. You're going to have out here, here's f1. And just to emphasize that f1 is much bigger than f0, I'm going to put like this kind of thing here. You know what that means. That's like a break in the graph, right? Big long axis, hidden complexity. Stuff could be going on in there that we don't care about. But anyway, out here, here's f1. OK, and here's f1 plus f0. And here's f1 minus f0. And I'm going to have a spectral line. By the way, the stems in spectra are called spectral lines for obvious reasons. And the height's going to be 1/4. And I'm going to have one at f1 plus f0 from this term, one at f1 minus f0. And then I'm going to have a symmetry, the conjugate symmetry thing going on. So minus f1 and minus f1 plus f0 and minus f1 minus f0. I'm going to have the same thing. All right, so why do we do this? Why did we figure out the spectrum here? Well, just for fun is part of it, but also because if you de-Euler this, you can think of it as the sum of two cosines, and here's where your trig identity actually came from. The sum of two cosines, one of them of frequency f1 plus f0, and one of frequency f1 minus f0. Observe that from Euler again, x of t is equal to 1/2 cosine 2 pi f1 plus f0 t plus 1/2 cosine 2 pi times f1 minus f0 t. So it's the sum of two cosines whose frequencies are close. Because f1 is so much bigger than f0. So why did I bother going through this and getting x of t in this form? That it would have been the result of our, if we had memorized our high school trig formulas, that's what we would have gotten. But we got it by going full Euler instead. And as a bonus, we got the spectrum. Because this is how you can hear this in real life. Like, how do you do this? You take an instrument, say, and you, I don't know. I'm trying to think of a specific instrument example. Like one guy in last fall's class played the viola in the Cornells. And so I said, oh, say you're tuning your viola and whatever. If you have two notes that are really close together and you play them at the same time, you hear that beat phenomenon. You hear the note that's kind of halfway in between them that's beating. And you can actually, you can hear this in real life on your musical instrument. So maybe we'll do that when we bring in the keyboard. So the idea here is that what happens when you add these two together is you hear, remember, the f0, or sorry, the f1 cosine, which is frequency halfway in between f1 plus and minus f0s, which are the two frequencies of the component summands in x of t, beating, quote unquote, at frequency f0. And this is easily demonstrated by taking two instruments that are slightly out of tune with each other. And you can do it on the viola, say. You say you're tuning one of the strings and you put your finger on the fret of the next one that's supposed to have the same frequency as the string you're tuning, and the one you're tuning is a little bit off. If you play those strings at the same time, you'll hear a beating sound. Okay, now, can you think, Alex, you're a music guy, so you can, what's a better example?
So, like, we're kind of out of time, but I could give an example from my phone with two pure sinusoids, and there's a high probability.
We're not out of time, by the way.
That I might make a quick demonstration and upload it to Canvas.
Oh, high probability. Well, let's make that closer to 1. How about that? Yeah. So people already uploaded like a web demo of Markov chains to my other course, Canvas, so, or to Piazza actually. So that's cool. But anyway, okay. So that's a beat signal, and the other example I want to consider, I have 35 seconds left according to that clock, which is wrong. I know it's wrong, so I'm cheating you out of part of your day. The other, I just want to leave you with the signal. And as I said, this is an example related to this one. So the other example is what I'm going to call an amplitude modulated sinusoid. And I avoided using the M word much when I was talking about the beat example. But this one is going to have something that always has a positive modulation envelope. And so what we're going to do is we're going to have, this is what it's going to look like. It's going to look like S of t times cosine 2 pi fc t. And this is going to be slowly varying. And fc is going to be big. And we're going to look at some specific examples of this. And we're going to see, and so this is slowly varying and always positive. We're going to see how this comes up. And does anyone know what fc, why the c on the fc? Preview of coming attractions. Why is it called fc? What kind of frequency is it? Never mind. Well, you can read the book. You can find out that way. That's a way to do it. OK.